So let's kick things off with the million-dollar question. When your lab report says your creatinine is exactly 1.00, is that the absolute, final, undeniable truth? Well, the answer might surprise you. It's a big no. And trust me, that's actually a very good thing. You see, a truly high-quality lab result isn't just one number, it's a range. That little plus or minus you see there, that's not a mistake. In fact, it's the hallmark of a quality lab. It's called measurement uncertainty, and it tells us just how confident we can be in that result. So, here's what we're going to cover. We'll break down what measurement uncertainty really is. We'll learn its language. We'll look at the two main ways labs figure it out, walk through a real-life calculation, and, most importantly, we'll see why this stuff matters from the lab bench all the way to the patient's bedside. All right, let's start with the absolute basics. What in the world are we even talking about when we say measurement uncertainty? Well, at its core, it's about accepting a simple truth. No measurement is ever perfect. So here's the formal definition. It's basically a range of values surrounding a result where we believe the true value is hiding with a certain level of confidence. So think of it less as an error and more as a confidence interval. It's all about quantifying the doubt so that a doctor can quantify their confidence. Now, to really get a handle on this, we need to speak the language. There are a few key terms that are the building blocks labs use to put together that final plus or minus number. Let's break them down. First up, we've got standard uncertainty, which we write with a lowercase u. This is kind of like the basic atom of doubt. For all practical purposes, just think of it as the standard deviation of the measurement. It's our starting point for everything else. And then we have its big brother, expanded uncertainty, with a capital U. Now this is the number that really matters to the doctor. It's what they actually see. We get it by taking that standard uncertainty and multiplying it by something called a coverage factor, which is usually just the number 2, to give us a really high level of confidence, typically 95%. Okay, so where does this uncertainty come from? Let's imagine we're throwing darts. Precision is all about how tight your grouping of darts is. You could have a really tight cluster way off to the left. That's high precision. This is your random error. Now, trueness or bias is how close the center of that cluster is to the bullseye. That's your systematic error. A good measurement uncertainty calculation has to account for both of these things. And we figure out these uncertainties in two ways. Type A uncertainty comes from the statistical data we generate right there in the lab, like running the same quality control sample over and over and seeing the variation. Type B, on the other hand, comes from outside information, like the spec sheet from the instrument manufacturer or the certificate that comes with the calibrator. You need both for the full picture. All right, so we know the lingo, but how do labs actually crunch the numbers and get that final value? Well, there are two main strategies they can use. Think of them as two different detective paths to get to the same answer. The bottom-up approach is like the Sherlock Holmes of uncertainty. It painstakingly identifies every single possible source of error, the pipette, the room temperature, the calibrator, you name it, and adds them all up. On the other hand, the top-down approach is more like a seasoned street detective. It looks at the lab's real-world data, mostly from quality control, to see what the total combined uncertainty looks like in practice. With that bottom-up method, you are literally an accountant for every tiny bit of doubt. You identify every source, you quantify it, you combine them all using a special formula, and then you expand it to get that 95% confidence. It's incredibly thorough, but man, it can get complicated fast. Now, the top-down method, which is way more common in clinical labs, is just so much more practical. It starts with the lab's own long-term quality control data to measure its precision, and then it factors in an estimate for bias. You combine those two main ingredients, expand the result, and you're good to go. Let's actually see how this works. Theory is one thing, but let's make this concrete. We're going to walk through how a lab calculates uncertainty for a test you see all the time. And you'll see exactly how all these ideas snap together. Okay, let's put on our lab coats. Imagine a patient's creatinine result comes back at 1.00 milligrams per deciliter. We're going to use that practical top-down approach to figure out the uncertainty that should go along with it. First things first, we need our data. The lab looks back at 6 months of its quality control records and sees that its precision, measured as the coefficient of variation, or CV, is 2%. That gives us our standard uncertainty for precision, 0.02. Then they account for any potential bias, estimating its uncertainty at 1%, which is 0.01.
Now, we have to combine them, and you can't just add them up. That'd be too easy, right? We use a cool little formula called the root sum of squares. You square each uncertainty component, add them together, and then take the square root of that total. In this case, that gives us a combined standard uncertainty of 0.022. But hold on, we're not quite finished. That's the standard uncertainty. To get the final number that a doctor can actually use, we need to create that 95% confidence interval. So we take our 0.022 and we multiply it by our coverage factor of 2, and that gives us 0.044. And there you have it. This is the final, complete result. The lab reports. Creatinine is 1.00 plus or minus 0.044 milligrams per deciliter. What this tells a doctor is that they can be 95% confident that the patient's true creatinine value is somewhere between 0.956 and 1.044. Now that's useful information.
So we've gone through all this math, but why? Why bother? Because this number is so much more than just a statistical footnote. It has a real, direct impact on taking care of patients. For starters, it helps the doctor decide if a small change in a patient's results over time is a real change or if it's just random noise. It's also how labs prove their testing methods are performing up to snuff. It backs up their daily quality control. And, this is a big one, it's a non-negotiable requirement for the lab to get and keep its accreditation. And I'm not kidding, this isn't just a suggestion, it's basically the law of the lab. The international gold standard for medical laboratories, ISO 15189, says it right there in black and white. Labs shall determine measurement uncertainty and make it available. It's a fundamental part of modern lab quality. This also means that calculating measurement uncertainty isn't something a lab just does once and then forgets about. Nope, it's a living, breathing part of the lab's entire quality system. You see, a lab has to recalculate its uncertainty whenever something important changes, like they get a new big batch of reagents, they recalibrate an instrument, or they tweak the testing method in any way. And the whole process, every step, has to be documented in their official procedures. It's a constant cycle of checking and rechecking.
Okay, let's boil all this down. If you remember nothing else, remember these 5 things. 1. MU is the confidence interval around a lab result. 2. Remember the 2 U's? Lowercase u is the standard uncertainty, and uppercase U is the expanded uncertainty that gets reported. 3. The top-down approach is the practical one, using real-world QC data. 4. Bottom-up is the super detailed dive into every single error source. And 5. The final result is always reported as the value plus or minus U.